So we're going to go slowly through this problem. We have that stone B has a mass of 17 kilograms and starts at rest. And then stone A, which has this mass of 19 kilograms, is slid towards stone B. So let's start with that. Here is stone A, and it is slid with some initial speed VI towards B. So here's A and here's B. And B starts at rest. And let's see, MA is 19 kilograms and M sub B is 17 kilograms. And we are told that the initial velocity of A is 0.2 meters per second. Okay, and so what happens next is that stone A hits stone B, and after the collision, stone A is moving at a speed of 0.05 meters per second at an angle of 20 degrees relative to the incoming direction. So this picture here is before the collision, and then here's a picture after the collision. And what I have is, let's say that this is the x-axis, this is the incoming direction, and so stone A is kind of moving in, oops, that's kind of like a 45-degree angle. Let's make it a 20-degree angle. So it's kind of moving in that direction. Let's call this VF. And this angle here, theta, is 20 degrees. Okay. And this is block A, so stone A. And so what happens to stone B? Well, if stone A got deflected upwards, then momentum has to be conserved. So there's something moving up. At the beginning, there was nothing moving up or down. So stone B is going to have to be moving down, but it's also probably going to be moving a little bit to the right. So it's going to be doing something like this, right? And we're not really sure what this velocity is or what this angle is. So let's call this angle phi, and let's call this velocity u. Oops, let's call this velocity here u. That's the velocity of stone B after the collision. So let me write this a little bit nicer here, before and after. Okay, and so the thing that I want you guys to notice is that there's a clear before and there's a clear after, right? And so whenever you have a problem that you have a clear before and a clear after, and you don't really care about what happens in the middle, or what happens in the middle is difficult. So like this collision, what exactly are those forces in there, that's hard. And so what we're going to do is we're going to use a conservation law that relates the beginning of the story, the before, to the end of the story, to the after, right? So in this case, right, whenever you have collisions, we're going to look at conservation of momentum. So we're going to look at the final momentum is equal to the initial momentum plus any external impulses. But in this case, there are no external impulses. It's just the stones hitting each other. There's nobody pulling or pushing on the stones. So this term is going to be 0. And so this is what we have. So we want to write this equation here. This equation is a vector equation. So this is true for the x-axis and for the y-axis. So let's go ahead and start going through that. So for the x-axis, final momentum. So I look at my final picture and I have MA, and the velocity along the x-axis is VF times cosine theta. Mass B is also moving along the x-axis, and it has a velocity of u cosine phi. Okay, and that is the total momentum in the after picture. So that's going to be equal to the initial momentum, so the total momentum along the x-axis in the initial picture, and that one's easy. That's going to be ma times the initial velocity. Same thing for the y-axis. Okay, so for the y-axis, I have that particle A, or stone A, is going up with this velocity VF of sine theta, whereas B is going down, so the velocity is downward. So I'm going to have minus M sub B times u sine phi. and that's going to be equal to the initial momentum, which if I look at my before picture, nothing is moving up or down. There is no momentum along the y-axis, so the initial momentum along the y-axis is just 0. So I have these two equations. These are the two equations that I want to solve. So let's try to solve these equations. So what I would like to do is I would like to solve for u, and I would like to solve for phi. And so I have this sine phi and I have this cosine phi, and that's kind of annoying. Let me go ahead and isolate these terms over here just to see what we can get, okay? So on the x-axis, the equation for the x-axis, I can get that u cosine phi is equal to MAVI minus MAVF cosine theta, and this whole thing is divided by m sub b. Actually, I'm going to keep the m sub b here. Let's keep it on the left hand side because it's going to make it a little bit easier to do the algebra. And let's isolate the mb. Let's isolate this term here on the left hand side of the equation from the y side equation. This is mb u sine phi, and this is equal to MAVF sine theta. So all I did is for this equation, I just moved this bit over to the other side, and for this equation, I just moved this bit to the other side, and I am left with these two equations. And so I can now try to solve for u and for b, and for phi, sorry. So let's solve, for example, for phi first. So I'm going to call this equation 1, and I'm going to call this equation 2. And notice what happens. If I take the ratio of 1 divided by 2, on the left-hand side, I'm going to get this divided by this. So the MB's will cancel, the U's will cancel, and I'm going to be left with sine of phi divided by cosine of phi. So that's going to be tangent of phi. And I got rid of that U, which I didn't know what it was. So that's beautiful. That's what I wanted to do. I wanted to get rid of one variable. So tan of phi is equal to MAVF sine theta divided by MAVI minus MAVF cos theta. And so this is my solution for the angle phi. How could I solve for u? Well, if we look at these equations, right, if we want to get rid of phi instead, one way to do that is that we know that sine squared plus cosine squared is equal to 1. And so that would get rid of those trig functions. So let's go ahead and square this equation, and add them together. So I'm going to do equation 1 squared plus equation 2 squared. So on the left-hand side, that gives me mb squared times u squared, and then sine squared plus cosine squared, that's 1, so that just simplifies to this term. And on the right-hand side, I'm going to get ma squared, vf squared, sine squared theta, plus MAVI minus MAVF cos theta, and this whole thing is squared. And so now all I need to do is divide by mb squared, so I get u squared is equal to 1 over ma squared divided by mb squared, and I'm going to get vf squared sine squared of theta plus vi squared minus vf cosine theta, this whole thing squared. And actually this square doesn't go here because the square is this square right here. So we close parentheses, and that is my final answer for the velocity of the stone. So at this point we can go ahead and we can plug in all of these numbers. I'm going to let you do that if you really want to. I don't really care about the numbers. this is how we solve the problem. We know MA, we know MB, we know the final speed of stone A, we know this angle, we know everything in this expression, and so we can calculate U.